Okay, so what I've brought for the experiment is this device here. It's called Analog Discovery 2. It's from a company called DIGILENT that somehow belongs to National Instruments. And it's essentially some, analog to digital converter or some data acquisition board that connects via USB. So this is a USB to the computer, and at the front, it has some interface where you can directly connect cables, or where you can connect such breakout boards like this one here. And as you can read, this says it's some analog discovery impedance analyzer. So this helps us to analyze impedances. And in general, you could connect something directly to this, to these terminals here, but this only works for small components. So what I usually do is I attach some more cables, and then I can connect like a breadboard. And on this breadboard, the simplest thing that I have prepared now is some rather large resistor. And so I can connect this to the resistor, and then we can measure the frequency dependent. And there you can see that it's already also blinking, and hopefully now it's connected to my computer. We can try to measure the frequency dependent impedance of a resistor. And so the impedance of a resistor is just the resistance. And yeah, in this case, it should not change with frequency. So now if we take this proper software here and go to impedance, and so now I have selected here that we have this adapter, and let's say we will start from maybe 100 Hertz up to 100 kilohertz of frequency. And so then what we will display is the magnitude of the impedance, right? This should be magnitude here, and here we get the phase. And so we measure impedance by magnitude and phase. And if I hit single, then we should get one of these measurements with 151 steps, for example. So what would you expect as a result in this case? A straight line. So let's see if this works. And so as you can see, we get a straight line. The auto scale, this is not working that nice here. How can I scale my amplitude? It's set to auto scale, but it's obviously not working that nicely, but because it's already at, but okay, if we rescale it a little bit, you can see, okay, it's a straight line, and we get 0 degree phase as usual for some resistor, because this is also what our function here tells us. Okay. So instead of a resistor, I could, of course, also add, or not add, replace it by some capacitor. And I have a rather large capacitor here. I think it's 0.22 microfarad, and this would work up to a frequency, up to a voltage of 1 kilovolt. So if I remove the resistor and add the capacitor, and I think now it's connected to the third and to the fourth. So like this, now we have some capacitor there, and I can also measure impedance by magnitude and phase of this capacitor. Before I hit run, what would you expect? a slope, and a slope like going up or going down. It should go down with frequency because this is what we discussed here. Impedance should go down with frequency and the phase should be, the phase is 1 over J, and J was 90 degree, 1 over J, that's why it should be should be 1 over e to j 90 degree. So it should be if I rewrite it like this, what should change with the angle here? It should be negative. Exactly. So we should get minus 90 degree. So let's see if this works. Let's do some single run. And then we see, okay, impedance goes down with frequency, and the phase angle is minus 90 degree. And then somehow goes up a bit. So interestingly, this works. Does not look too bad. If we increase the frequency, go to 100, from 100 kilohertz to 1 megahertz. And if I press this button once again, so impedance is going down with frequency, is going down, phase shift is minus 90 degree. But yeah, then we hit some minimum, and then the impedance is going up once again, and also the phase angle goes up. So why is this? In practice, unfortunately, the connecting cables here, of course, they also have some inductance. And it's like the loop inductance of this loop that is formed by my cables here. And so these cables make that if we go to frequencies of 1 megahertz, that this capacitor will not act as a capacitor anymore, but more like an inductor. Okay, so then the last thing that I have, and I hope it really is one, is some inductor. Just very small one. And so if I remove the capacitor and instead of this, connect this inductor. And I think it's some inductor, maybe it's not, but we will see in a second. Add this inductor and go back to the measurement program. And if I hit the run button, what would you expect? What should happen? Exactly. We should get some increasing slope according to our formulas that we have here. And J is 90 degree of phase angle. So let's see if this works. And obviously it does not work. This is not some inductor. This is some resistor. Oh, no, maybe not. It is some inductor. So it is some inductor because here impedance is going up with frequency and we have a phase shift of 90 degree. But for frequencies below 10 kilohertz here maybe, especially below 1 kilohertz, we have 0 degree phase shift and we have some constant magnitude of the impedance. Why does this happen? Because what is the inductor made of? If we would be able to take a look into the inside of this inductor, It's made out of a wire. Take a wire and wound a wire. I think, yeah, maybe I have some, maybe we can see if we can measure some different inductor. So this inductor is made out of a wire, and the wire, of course, has resistance. And so if the frequency is very small, then, and if the inductance is not too high, then the inductive impedance, let's say, is smaller in comparison with the resistance. And that's why we more or less only measure the resistance of this inductor. So this is very typical, that for some, yeah, it's like a series connection of R and J omega L. And so at low frequencies, we measure the R. At high frequencies, we measure the J omega L. At low frequencies, we have 0 degree phase shift. At high frequencies, we go up to 90 degree phase shift. Okay. So maybe what else we can try is I got some new samples from Würth Elektronik, and so I'm not sure about which is what here, but so you can see that there's something like with 10,000 microhenry, 1,000 microhenry, and another 1,000 microhenry or 1 millihenry. And these are how these coils look like. They are in their original packaging. And so this is the one that is labeled with the 100 difficult to see. There's the reflection 102. This is the largest one. I think this is probably the top one here that can handle the most current. 0.5 ampere, has 1.8 ohm of resistance and 1,000 microhenry of inductance. Unfortunately, this does not connect to my breadboard, so I need more adapter cables going out of the breadboard, going into the breadboard. So let's see if we can try to fix this here. So this connects to this side. And this connects to the other side. Okay, it's not nice, but it's somehow connected. And if I hit single again, we should see the same behavior. It's a bit more resistance, but we are already probably at too high frequencies to measure just the DC part, because we already have some kind of more than 10 degree of phase shift here. So if I go to smaller frequencies, if we start at 10 Hertz, and if we go to even higher frequencies and start to end at 10 megahertz, and if I hit run once again, then it will take some time, especially at the low frequencies, to do this measurement. But then we can see, okay, we start with something like 2.5 to 3 ohm, a bit more than the advertised 1.8 ohm in this case, but this is probably due to my fixtures here, right? The many additional cables that I've attached there. And so now the measurement should also be a little quicker. And so then if we further go up in frequency, impedance goes up with frequency, phase shift goes to 90 degree, and then something interesting happens. So the impedance gets rather high, and then the impedance goes down with frequency again. And it really looks like what we had before for the capacitor, that it decreases with frequency. And if we take a look at the phase shift is also at minus 90 degree. So in this frequency range, the inductor, the coil that we have here, I mean, here you can really see the wire that is wound to this inductor. This coil does not behave like an inductance anymore. It behaves like a capacitance. Why does this happen? It's the parasitic capacitance between the windings. So we have many, many windings and they are very, very close together. So it's like lots of small plate capacitors that are close to each other and that form some kind of capacitance inside this inductor. And this is what can be measured here between or above a couple of megahertz, or at least at 10 megahertz, it's very pronounced, this behavior. Okay, and so this is a quite nice summary and demo of this impedances, frequency-dependent impedances of resistance, capacitance, and inductance. The last thing that we can maybe do for the inductance here is, of course, we could also measure not only impedance, but inductance. And so if I scale and auto scale once again, and maybe if I just only measure in this range where we have some nice inductance between 1 kilohertz, which was somewhere here in the range, and maybe up to 1 megahertz or maybe up to 100 kilohertz, and just redo this measurement, then we see, okay, the inductance of this inductor is really 1 millihenry or 1000 microhenry, the value that was also announced here on the sticker from the sample. And if I remove the inductor once again and connect the capacitor and do a last measurement with this capacitor, measuring capacitance and not inductance, and hit single, then we need to look at the scale here. So this is nanofarad, and it says 200, something like 220 nanofarad, and this is also what fits to the 0.22, and the micro is missing there, but capacitors are usually given in microfarads. So yeah, this also nicely fits to what we measure here with this impedance meter or impedance analyzer. So this analog discovery 2 impedance analyzer is a very nice instrument to check this frequency dependent behavior of components.